G'day everyone, how you going? And a special hello to Anh and Jiwon who are missing my class today. It's okay, I don't hold it against you. I understand it. I'm not very important. I get it. It's okay. But hey, I did this video just for you girls. The boys are here. You girls, that's okay. Let's move on. Two things I want to do today. One is to talk about intercept collision, and one is the vector equation of the sphere. Leave this one for now, we get there in a minute. Intercept collision, 3D, we're in 3D vectors. Think about this. If I have an object, a body, particle, whatever, and it's sitting here, and it's traveling in that direction. So here we go, there it is. And I have another one that is sitting over here somewhere and traveling in that direction. Now, you can probably see that if both of them are moving at the same rate, same speed, same velocity, then they're going to collide. But if this one was moving slow and this one was moving fast, then they're probably going to do that, aren't they? Or the reverse of that. Or perhaps if the direction that they're pointing in, I'll exaggerate it, that one's way up there and that one's down like that, even if at some point in time one is above each other, they're not going to collide. So this whole idea of intercept collision is looking at things in 3D space. Will they collide? Now you might think, who cares? Why does this matter? Well, if you've ever taken a trip on a plane, then you're glad that someone worked all this out, because air traffic controllers will ensure that two planes are not going to do this. If they are likely to do that because of where they're heading, they will tell one plane to speed up and the other to slow down so they miss. Or they will give the planes different height ranges to work in. So they'll say, as this one takes off, they'll say, climb to 8,000 feet and hold. So that the person will do that. And this one taking off some other airport might be a long way on the ground, but in the air, of course, things happen a lot quicker. Climb and hold at 8,000 feet. Climb and hold at 12,000 feet. And then once they've passed, this plane can then come up to cruising altitude at 12,000 feet or whatever. So the whole idea is so things don't crash into each other. But sometimes we want them to crash into each other. I don't like talking about war and things like that. But in war, if there's a plane flying over there and it's not one of yours, you want to shoot it down, you want to shoot a missile so it hits that plane. Now if the plane's there at the moment, you don't want to aim at the plane, because by the time the missile gets there, the plane's moved on. So you've actually got to fire in front of it so that this happens. Right? So sometimes you want to hit the thing, most of the time you don't. So what are we doing? Well, I've done a diagram here in 2D effectively. Here we go, here are my two starting positions, and here's my velocity of B, velocity of A, which that's fine. Now, recognize P. Now, the book doesn't use P, it just uses R, but I used R over here already. I wanted to differentiate. See P as the position of my particle at any time. R is the starting point of my particle. V is the velocity. Well, I can write this equation here. The particle A will be at any point, starting point, plus lambda, time really, but we usually use lambda. Lambda, lots of velocity. That's really just saying start here, and you're heading in this direction. Well, after 3 seconds you're here, after 5 seconds you're here. That's all that is. Same for the other one. And remember that all of these are either velocities or position. And if we're in 3D, then we've got three of them, X, Y, Z, I, J, K. So just recognize that's three things in each of these, but the lambda is just a single thing. That's time, if you like, so that's just a single number. Okay? Can be positive and negative, but a single number. So if we want to see whether these things collide, what we've got to recognize is that PA must equal PB at some point. X, Y, and Z, I, J, and K that we get out of this equation must be the same as out of this equation, because that will mean they're in the same point in space at that time. If only two of these are the same and one is different, then that's this situation where they're going to go through the same vertical point but at different heights. Or if you rearrange that the other way so you have the heights are the same and the x dimension's the same, but the y dimension's different. So it's hard to do the same way, but the same situation as that, basically turned this way and then turned that way. So if only two of them match, it's not going to collide. All three have to. How do we do it? Well, we just solve for the I component. Remembering there's three here, we solve for the I component just by picking out the i's of this one and the i's of this one. So I've denoted this as RAI, the starting point in terms of the I component, plus lambda VAI. That will tell you the value or the position in terms of I of particle A, the position in terms of I in particle B, and you'll have some lambdas flowing through there. You would then solve for lambda, get some answer out. Who cares what it is for now? Let's say it comes out to 5. That would mean after 5 seconds, assuming it's time, that the I components of these two particles are the same. You would do the same setup, but with the J's, and if that one came out to 5, then that at this point would say that they might be doing that. They might not as well, but they might be doing that. Okay? Then when we get this one, we solve this one and get 5 as well. That says they are going to collide through the same point in space, and hence they're going to collide or intercept. So it's a matter of just picking out the I's, solving, getting an answer. Pick out the J's, solve, get an answer. Do the K's, and if they're all the same, boom, they must have collided. So this is the start of our intercept collision idea. The questions at the early stage aren't too bad. We then, when we realise that they don't collide, there's another step, gets a bit complex, where we decide how far apart they are at their closest point. Okay, so nearest point. So they might not collide, but at some point, there's the shortest distance they are together. Now, if you were going to, I don't know, throw something out of the plane or at another plane or something, I don't know why you would, then you want to throw that at the closest point. Okay, so there's a range of reasons why you might want to know that. That's where this goes to. It sort of says, well, okay, now that we know that they don't collide because, say, these are different, how do we figure out how far apart they are at the closest point? That's that part. Let's get on to vector equations of the sphere. Lots of stuff here. Right, first, let's go back to a circle, okay? If we had a circle, 2 dimensions, right? For those playing along at home, here we go, and we've got a circle somewhere there. Now, the definition of a circle is the set of equidistant points from another point. Set of equidistant points from another point. Because there's my other point, and all of these are the same. Of course, it's the radius. All of them are the same. So this here, this is saying choose any point you like, minus away the center. Let's say that that's 2 and that's 3. Might not quite look like it on the diagram, but choose any point, subtract away the center, and then work out the absolute value of it. So if I choose a point that's not going to be on the circle, let me choose a point here. So that value there, let's say that's, I'm going to exaggerate here, 10, 15. I'm exaggerating so I know it's well outside of it. So 10, 15 would go in here. 1 minus the other, 1 minus the other, square it all. And if that value came out to 5, that would mean that point was on the circle. If it didn't come out to 5 like this would, it's not on the circle. Okay? If it's greater than 5, it's outside of the circle. If it's less than 5, it's inside the circle. Right? Now then, let's go with something a little more realistic. Let's go with something like, what have we got? 5, I'm going to cheat here. I'm going to go with 7, 3. That point right there. It's the point 7, 3. Now I've cheated there because I know that's 5. Right? So if I put 7, 3 in here, well, that bottom line is 3 minus 3, that's 0. 0 squared is still 0. 7 minus 2 is 5. 5 squared, absolute value, square rooted, is going to be 5. So because that works, that says the point 0.73 is on the circle. That's a bit of a recap of this whole circle idea, but remember that to work out a circle or to give a definition of a circle, we're looking at the difference between 2 points, A point and the center, equaling the radius. Now, if we want to turn a vector equation into a Cartesian equation, we just throw xy in for that point R. Then we get x minus 2 squared, y minus 3 squared, 5 squared. There's my circle equation as a Cartesian equation. Now all of that is the precursor for 3 dimensions because it's exactly the same, just that there's another number there. Because now we're x, y and z, I, j, k. So there's another number there, but everything that I said here works exactly the same. And I can turn that into my Cartesian equation. It's just got an extra bit on it. That's all for the x, y, z dynamic. So this is circles. This is in 3 dimensions, so it's a sphere that we're looking at, not a circle. But essentially, what you did here, do here. Hope this one's helped, Anh and Jiwon. I hope you enjoy your day off, relaxing, kicking back. Catch you later.